All right, welcome back to SGLang Office Hour. Today we're going to have people from Boson. They just launched a new TTS. I think that model is right now is probably the most popular TTS model downloaded at Hugging Face in the past few days. We have Ke and Huapeng joining us in the live stream room. So I'll start with Ke. So Ke, can you introduce you to us? A little bit
Yeah, hello everyone. I'm Ke, and currently I'm a research scientist at Boson AI. I'm part of the team that developing our Higgs Audio V3 TTS.
Amazing. Huapeng, how about you?
Hi everyone, I'm Huapeng. Actually, in the past, I'm the developer at SGLang and Mass, and now I'm the member of technical staff at Boson AI, and I have implemented many stuff like training and inference with SGLang, and yeah, it's very glad to be here today.
Amazing. So before we get started, so can either one of you tell us what is the Higgs TTS? What is different from the normal TTS? Is that something you try to do differently than the other people who try to train a TTS?
Yeah, I think this question is related to why we want to have the TTS. I mean, the TTS is like a part of our whole audio verse. Like we have text to speech, speech to text, and we have avatars. And our text to speech is just we want to cover as many as language that we can. Like we have more than 100 languages supported, and also we want to increase the richness of our voice cloning. That means we add a lot of support to adding the emotional richness to our system to make the machine sounds more like human.
Amazing. Huapeng, I know you're part of the SGLang-Omni team. So can you quickly tell us what's the SGLang-Omni and
Yeah, thanks, Haokong. And I think everyone knows SGLang, right? But SGLang is mainly for the but actually for the multimodal, especially for the audio output, we need to maintain the different stage for different process. And I will give a comparison later in my today's presentation and give a more detailed explanation. And I think both are very useful, and especially for Boson in SGLang-Omni is very useful for our inference and our production level TTS service. Yeah, thanks.
Great. I think we're done with the roaming up, and I think you have the stage. I think Ke will start with the talk today. Yeah.
Yep. Yeah, I think I'm ready to share the screen.
Yes, let me control the screen sharing here. Yes, 1 second. Yeah, should be doing that. Okay, perfect. Yeah, you're good to go.
Great. Yeah, as I mentioned in the intro, today we want to share the process or the experience that we have when we built the fast and modern voice cloning, that is Higgs Audio V3 TTS. Because the text model is very popular recently, but we believe that voice is definitely the interface for the future, and it's belong to the open ecosystem. So I know a lot of participants today, they are the developers, and everyone use Cloud Coda or Codex or any kind of AI agents. So in the first page, I just put a document here that everyone could visit. And if you do not want to go into details, but you want your agents know more about us, just copy paste this line to your website or tell your favorite AI coding assistant and ask it to do anything for you. And if you want to know more a little bit deeper, and then we could continue. And here is intro page to our model. I mean, as I mentioned at the very beginning, we support over 100 languages, and we enables very rich control over the generated speech by the inline tagging. Here, I just show three different aspects that our tagging system support. And the developers could dynamically adjust the emotion procedure and the pacing in the middle of the sentence. And this video is just 1 minute, and it shows a lot of functionalities of our model.
Hey, how can I help you? Hey, how can I help you? Same voice, same words, and a completely different presence. Welcome to Higgs Audio V3. I was built for chat native voice, real-time, expressive, and controllable. I can be happy. I also can be sad. I can slow things down or quickly speed things up.
Yeah, and this is a video like showing the tagging functionality of our text-to-speech model. And you will notice that there's actually an avatar saying those generated voice out. And this is also one of our products that you could directly experience at this link. And in the meantime, we also prepare the different recipes for the people with different needs. And we already have our own API that you could test your own voice. And the good news is that it's recently free. So you could just apply an API key in our website and try your own voice. And if you are enthusiastic about the technology and the model, and you have your own GPU, you could just deploy locally with our open source suite. And I tested on my own with the support of the third party. You could even run it on your MacBook. And if you are a researcher that's interested in the details of our model, you could check our model card on the Hugging Face. And of course, we have a short technical blog post that we cover all those above things into this blog so that you could find any resource that you need there. And we also put some evaluation there. And for today's agenda, and since I already provide a lot of links to you, I don't want to waste your time to repeat all the things that we have already written in the agents MD file. And we want to introduce something behind the model that we developed from the perspective of model evaluation and inference. So I will first talk about the model and the evaluation part. And for the text to TTS, the text to speech, actually this is a quite old topic that exists for many years. And people may ask, since we already could do a very good text to speech a few years ago, why do we still focusing on this topic and spend large amount of human and the machine resources on this? The answer is that we need a good TTS model that could really express the human's emotion. And this axis just shows the scale of the parameter in different models. As you could see, the smallest voice clone model is just 80 parameters. And the largest one is the 8 billion. So the difference between the smallest one and largest one is just how the richness that we want our voice be. And for the small model, it may only able to clone the several persons' audio, and their sound is already baked in the weights of the model. And when the number of parameters increases, the model could clone anyone's voice in the zero shot. And in the meantime, we could add more emotional information into the model. And of course, there are smaller models that might less than 30 million parameters or larger than 8 billion. But for the smaller sized one, they usually just support one or two voice. And for the larger one, it usually goes to the voice agent that could not only speak things out, but also understanding and do some inference. But that is all of the scope that we are talking about today. And this is about the number of parameters. And about the methods, it also differs a lot. I mean, several years ago, people may focus on the mail-based methods. And after that, people start to use flow matching or diffusion methods that have been very mature in the image domain or in the music generation domain to the text generation. And there are a bunch of work. And after that, people notice that the multimodality that we adding the modality of the audio and the language has a huge potential. And so there comes the autoregressive language model with either the flow and diffusion module and the codec version. So the difference of these two is actually mainly located in the encoder and the decoder thing. So we know that flow and diffusion, they usually handle the continuous feature. And for the codec one, we usually want to map the continuous waveform or mail spectrum to the discrete space so that it could have a closer connection to the text. Because we know that in the pure text, we have the discrete text tokens. But both of those methods, we both rely on the autoregressive language model. And so our Higgs V3 TTS model just belong to the autoregressive model, autoregressive language model, and the codec part. And our model architecture actually is very simple. So we know that we want to do a voice clone task, right? So to achieve the goal, our input should be your original voice, where I call it the reference audio here. And in the meantime, you need to see that original voice have some text, so you also have the reference text. And to clone it, you have something that you want to see, that is the target text. And then the output will be the cloned voice. And those three inputs and the outputs just corresponding to the text tokens, the reference text, reference audio, and the outputs audio tokens here. Basically, we're still training an autoregressive model, but the difference between the audio language model is that we use audio tokens. But we all know that the audio are the waveforms. So that's why we have an actual tokenizer that we encode the waveform into the audio tokens first. And after we generate the audio tokens, we decode use the tokenizer to map the discrete tokens back to the waveform space. So those tokenizer and our autoregressive decoder backbone, these two modules just they together becomes our whole model. And when we do the training, of course, we follow what other people did in on the markets. We first train the tokenizer first, and after that, we just fix it and tuning the autoregressive decoder backbone to map the audio tokens to the text tokens. And because of that, here I want to show how our audio tokenizer is designed. So basically, it's a autoencoder architecture with the quantization layer in between. And here you will notice a module called the RVQ, that is residue vector quantization. And our encoder part is simple. We have two parts. One is the semantic encoder and the acoustic encoder. And this semantic encoder, it's a frozen wave-to-vect model to try to map the waveform into the semantic latent space. And we have a learned acoustic encoder, which is a CNN-based one. And after we extract the feature from both the semantic head and the acoustic set, and we concatenate those together, and then we use the residue vector quantization to quantize those continuous features into the discrete tokens. And we also have a decoder that, on the one hand, we try to recover the semantic information from the quantized features, and in the meantime, we need to reconstruct the waveform. So encoder, quantizer, and the decoder, those three parts just bring us our codec. And a little bit more details about our tokenizer is like the total parameters is around 200 million, but almost half of them come from the semantic teacher. And our decoder is just around 20 million parameters. So when we try to do the decode from the audio tokens, actually the cost of doing the decoding is very low. And for the quantizer part, we use 8-layer residue vector quantization. And for 1 second of the input audio, we might generate 25 frames. And for each frame, it has 8 codebook. Okay, so this is about the details of our tokenizer. And then we go back to the whole architecture. Since you already know how to convert the waveform to the audio tokens, then you could just forget what the tokenizer is and just treat everything as the tokens. We have the text tokens, audio tokens, and we have the backbone that is a 4 billion autoregressive model, and with those hyperparameters that are listed in this table. Next thing for us is just to train the decoder backbone end to end, and then we could get the things that we want, which is a text-to-speech model. And there's a little bit more that I want to talk about that a lot of people might not understand very well. And it also takes me a little bit of time to understand it when I first learned the text-to-speech and autoregressive language audio models, that is the delay pattern. As I mentioned before, when we have the 1 second of the waveform audio, we have the 25 frames, and each frame we need to use 8 codebook to represent that frame. So to summarize, for 1 second of the waveform, we have at least 200 tokens to represent that one. So this is actually a little bit counterintuitive, because in the text domain, for each text token, we just have one code, and all the text tokens, they share the similar codebook. But in the audio setting, why do we have 8 codebooks? And how to handle that 8 codebook will be problematic. The reason that we want to have the 8 code book is that just we hope that quantizer layout to preserve as much as information that we want. But then the problem is how we handle that long code book. So one naive solution is, okay, we generate each code book one by one. But that means if our max length capacity of the language model is just 8,000, we could generate very limited time frames of our audio. Because for each frame, it needs like 8 codebook, right? And here in this demo, I treat the codebook size as 4, as you could see. So this is a flattened way, that is the most naive way, which consumes your GPUs a lot. So instead, we borrow the ideas of the delay pattern. And the high-level idea of the delay pattern is, in the first time frame, you're still doing the similar thing as we do in the flattened way. But when we do the second round of generation, we not only generate the second codebook of the first frame, we also start to generate the first codebook of the second frame. And then at the step 3, we generate the first codebook from time step 1, the second codebook from time step 2, and the third codebook from the time step 3. And following this way, of course, there's some information loss because we already start to generate the second frame without all the information from the first frame. But the advantage is that it saves us quite a bit of resources, because it's like we have a multi-channel output heads that could generate multiple tokens at the same time. So that gives us the room to generate the longer audios. Yeah, and I think this covers mainly about our modeling side, the tokenizer and the autoregressive model. And for the evaluation part, I'm not preparing to show, the numbers of a model, like we reach the state of art in this domain and on this metric. I just want to share with you like the evaluation side that we conduct our model on. And the one side is we want to test the fidelity of the voice clone. And here we benchmark our model on some industrial standard benchmark like CTTS, which covers English and the Chinese, and the Causey V3. They have an evaluation size that cover less than 10 different languages, and the Minimax multilingual evaluation, it covers around 20 to 30 different languages. And because our model supports 111 languages, so we built our own Higgs multilingual evaluation set, and I hope this could be public soon. And this on this data set, we mainly calculate the word error rate, the speaker similarity of the voice clone task. But you will notice that the word error rate and the speaker similarity is not necessary, because our model also supports a lot of other things like the emotional control. Here brings us another evaluation task, which called the emergent TTS evaluation. I think this is a benchmark that our company released last year. And in this benchmark, it supports 6 different aspects, from the emotion to paralinguistic to foreign words, questions, and syntax, and the complex pronunciation. And the evaluation metric here is just not just directly calculating those metrics, but instead we try to compare the win rate between different models and to see which one is better, because all those kind of things are kind of subjective, and you could not easily to be evaluated by those hard metrics. So using those 2 different aspects, we try to benchmark our model in diverse but far away to all the competitors on the market. And if you really want to know those numbers, you could just check our Hugging Face and our blogs, and then you will know more details about those. Okay, so let's cover the model and evaluation part, and now I will hand it over to my colleague Huapeng, and who did a lot of things to try to optimize our model to make it fast.
Sure. Welcome, Huapeng. I'm going to control the slide right now. Give me a second.
Okay. And yeah, can anyone see the screen? How long can you see the screen?
I cannot see that. You probably need to share. Oh yeah, it's going up. Okay. Oh yeah, perfect. Yeah, go ahead.
Yeah. Okay. And thanks for my great colleague Ke, and who gives a lot of details and introduction for our model and tokenether. And I guess you guys have some basic understanding for the TTS about how it works and why it works so well. And I will give another presentation about the inference, because I think basically for the model today we get two parts. One is training, and for training we get a good checkpoint for the model which can generate good results. And another is inference. And for the inference, especially in the audio, it's like a bottleneck for many audio model. Just imagine you use Siri, you find that it's very slow, and so I think it's a task for both Boson AI and the community. And this Higgs Audio V3, which is TTS V3, is just like a milestone for both the Boson AI side and the community side, which can want to push the audio output to be more frontier. Yeah, that's my intro. And here you can see the top here. We get the microsecond world, which we want to make the speech faster than sound. The reason behind the title is just maybe it's two-way. The second is actually the audio model is very, very small. So basically the inference is already very fast. And the second is we want to use the SGLang-Omni to make it faster. Yeah, and actually here you can see the results. The first is RTF. What is RTF? It's just like a real-time factor. If you can generate 1 second audio in 1 second, the RTF will be 1. And if you can generate 10 audios per second in 1 second, it will be 0.1. So the number is lower, the better. And after both the Boson AI side and the community side, the hard work, we get in one H100, we can generate 60 audio second in 1 second, which is very high throughput. Yeah, and before that, and as Haogang mentioned in the beginning, what is SGLang-Omni? Why do we choose SGLang-Omni? Actually, I have the same concern before, because we already have a which is very popular and dominating inference framework in like SGLang. And so why do we need to make a SGLang-Omni? I think the first reason is from the model itself. The TTS model is not an LLM, and as just my colleague Ke mentioned, we have a tokenether, which is tokenether in the beginning, which is encode, and the tokenether at last, which is decode, which makes the system more complex, because everyone knows that in the text field, we do not have tokenether. We have tokenether, but it's just like a rule-based like BPE, right? And it's just like as you can see in the animation here, here is a pipe which consistently send off the token. But actually, you can see in the right one, we have encoder AR, which is autoregressive, just like the text, and we have get a vocoder, And after that, we get a waveform for the audio waveform. So from this different model architecture, we do need a different framework for inference, because if not, the SGLang main wrapper will be very, verbose, and we cannot support that easily. And I think that's the story of SGLang-Omni. And another thing is like for the Omni model, it has more stage and the process, like the video and the image, like the Q3 Omni and something like that. And and I think but by the way, the SGLang and the SGLang does not contradict with each other. It's just like a win-win. And I think the main property of the SGLang-Omni is the multi-stage and the asynchronous. And you can see in the animation here, you can see in the bottom image, if you get the request A, which enter the encoder, decoder, AR decoder, and the vocoder, the request B will be blocked because it does not have the same stage with the request A, so it cannot be batched together. But actually, from this characteristic, we want to divide the different stage into different stage, which is different process. And in different process, we can make them to be batched and respect each stage characteristic. So the first thing is that we get a rat scheduler in rat stage. For example, everyone knows continuous batching, right? Which can dynamically pick up the request and make them to be a batch. But actually, it's not in the case for the pre-processing, right? Because it's just like some CPU function. You can easily batch them together, and so we need the threaded safe, simple scheduler. And it's also not in the case for the encoder and the vocoder, because in the vocoder and the encoder, you can easily batch them together and batch process them. You do not need to do some trick like a continuous batching. And the second is that you can treat each stage more flexibly. You can give each stage a different config. And the third is like in each stage it's very easy to communicate. One of the communication is the control, which we can use ZMQ. It's implemented by SGLang-Omni, ZMQ to control the control message and use the SHM or NCCL for the real data transfer. Yeah, and from that, we can divide our TTS model into 4 different stages. One is like pre-processing. It's just like convert different audio format, like maybe mail form or something like that. It's a CPU function. And the second is audio encoder, and it's the second half of the tokenizer which just introduced. And the third is like an AR engine, and it's a Q3 4B backbone. It's the main time-consuming part of the TTS model, and actually it's the core and the hard part, but in the inference, but we can directly use them from SGLang. And the first part is the vocoder. It's just like the final step. You can use the audio token which generated by the AI engine to be the real waveform. And here is the delay pattern which made by Cloud to just show the capability of the Fable 5. Yeah. And okay, and let's move on for the stage by stage optimization. Actually, before the stage by stage optimization, I want to thank for the community which does a lot of optimization and profiling before that, so we can see which stage costs more, and we can use different strategy for different stage. And here is a roadmap. You can just search for the number of the issue here, which is like the roadmap for optimizing the Higgs model. And the first one is like a pre-processing. Actually, you do not want to use the CPU to get the GPU like a trick. So CPU can get a CPU scheduler, which is a threaded safe scheduler. and it's very simple by a thread pool. And second is the encoder. Actually, as the title said, we want to make the fastest compute, but actually the fastest compute is the no compute. So the first way is like we want to reuse anything we can reuse at our most. If we actually the reference audio, which is the audio we want to clone, is not so much. Maybe OpenAI just like provide maybe 20 voice you can clone. So in a limited scenario, actually you can cache the reference audio. And you can see in the graph here, the request 1, which is reference audio A, and request 2 is also reference audio A, and it does not need to encode it itself. It can be just cached. And the second is like the touch compile, because as Ke just mentioned, in the tokenizer you have different layer like CNN, like convolution, and layer long, and it's just like some small kernels. And if you want to run the forward just like in PyTorch, it will have some small gap between them. You can just say the eager way of that. But actually, PyTorch has some easyable use way like touch compile. You can touch compile them to automatically pick some of them to be fuse the kernel. And we can just like have some free gain. And the third one is the AI engine. And the AI engine, I think, is the most important part, and is the most part benefited by the SGLang-Omni, because SGLang is already a very fast engine, right? And we can actually reuse many tricks from SGLang, like just like the page attention, because everyone know that we can make the KV cache block into a block, so we do not have so many fragments. We get a better memory allocation, and actually use the engine, we can have the gain for free. And the second one is the main contribution of the SGLang, which is Redis cache, and actually support Redis cache in a text engine is not so easy. But SGLang provide an interface called extra key, and we can, if we get the same voice, we can hash the voice to a same hash, and the extra key is the same, so we do not need to prefill the same request. So we can, as we just mentioned, the best compute is no compute, so we can decrease the prefill time. And there is another some optimization, and actually I want to point out the CUDA graph is the most enhancement we can get from the optimization. So what is CUDA graph? The concept is a little bit maybe make everyone afraid, but it's the idea is very simple, because in the decoding step we are like a token by token, right? So in each token we need to launch the kernel next, which is operated by CPU. But actually you need to do the kernel launch every step, and it's very time consuming. But another trick which has already popular in the SGLang or beyond the text engine is like you can capture the CUDA graph first, then you can just replay the CUDA graph. You not need to launch and gather kernel graph, and it's the most gain we can we can get from the optimization. But actually, for supporting this in the TTS is not so easy, because in SGLang or VM, you can capture the different batch size of the input first, and then you need to maintain the different tensor to be the same chip. But actually, I will question that in the delay pattern, there are some different states, like you need to maintain a state machine for the state like in unchanged the shape. So we modify the delay pattern a little bit to make it consistent and can be accepted by the clock graph. And the first one is also a common strategy in SGLang, which is zero overhead scheduler. And actually, when you want to compute the input, just like the first party, which is the sync, you compute then schedule, which is just like a classical pattern, which is producer and the consumer. You produce some food from producer, the consumer consumes that, and the producer continue to produce. But actually, it's very easy to like them to overlap with themselves. You can prefetch some input before the consumer consume that, so we get some free gain from that. Let's move on for the vocoder. Actually, in the vocoder, the main part we want to highlight, which is the streaming. As you know, in the text, the streaming is native. You can just make the text token by token, and in the token by token process, you can just return them. But it's not in the case for the audio, because in the audio, you need to get enough token to generate and synthesize a comfortable audio. And actually, in the different audio, if you stream them by chunk, you will get some stuck in the middle because it's not so comfortable. So we got a good strategy, which is you can see in the window protocol here. After we generated some numbers of chunk, we can use a window, like a sliding window, to cap them. And in the next window, we will have some overlap in the middle, like this one. And we want to discard some tail because it's not so strong enough. So in this way, we can get a result like this. Non-streaming versus streaming. We do not need to wait the audio to be generated already, so we can submit the audio. So in this way, we can decrease the TTFB, which is time to the first audio bytes, very quickly. And here, actually, I made a live demo for the clone voice. It's very simple, just like it's just like voice clone, and let me just record it. It's just like a voice clone, but you can feel that you have different output for the non-streaming and streaming mode. And I guess my clone is enough, so I can generate. So let's wait for a few seconds. So it's just like basically cloning my. Hello, this is my voice, cloned by Higgs Audio V3 and served by SGLang-Omni. The streaming version of this sentence started playing before the non-streaming one even finished generating. Yeah. Hello. Just like a clone my voice. And if you use the streaming. Hello. This is my voice, cloned by Higgs Audio V3 and served by SGLang-Omni. The streaming version of this sentence started playing before the non-streaming one even finished generating. Yeah. So here is the last, which is the overall performance. And you can see we get different results with different concurrency, and luckily we get a good result for the concurrency 16, which means you have 16 requests in the same time. You can, in this case, you can generate 60 seconds, and the RTF is very slow, which means the latency for each user is very slow. And here is some benchmark for our model, and here we come to the last. Here is a code from I don't know where. And actually before that, I want to thanks for the colleagues from Boson AI, who make the good model, and actually the model itself has been the #1 trend in the TTS in Hugging Face, and the number 6 in all the model, which I think is very good, and it's my first time to do the model release like this. And the second is I want to thank for the SGLang community, which does a lot of optimization, and Chen Yang and Haoguan to support for the collaboration for the SGLang and Boson. Yeah, that's my presentation. Oh.
This is amazing. Actually, I'm surprised. I just have love to know, like, because the slide I just saw is probably just one of the most beautiful slides I've ever seen. Are you use Cloud Design for that, or?
Yeah, Cloud Fable 5. And I just actually the reason is that I want to make some animation, and in the beginning I want to make them by hand, but when I'm making them, I feel the time is not enough, so I just use Cloud. And it's better than
looks
what
very
I thought.
good. It looks very professional, like someone actually making that for a very long
Okay.
time. And I was also expecting like you at the end saying, "Oh, all the audio was like generated by Boson TTX." Next time, probably you can do that.
Yeah.
Yeah. I think you're going to have
And here is
final...
a speaker for Boson and SGLang.
Oh, that's so cool. Oh, I think you're going to like share a little bit more.
Yeah.
Okay. Yeah. Let's switch to the final slide. Yeah.
Yeah, and I think as Huapeng mentioned, is we have a lot of people like working on this open source project, and it's us honor to represent them to present here. And also, I think our model has been released around 2 weeks, and we also received some good feedback from the community, and we have already saw the community support on the Confi UI and MLX audio. The first one, I think, is just a better realization and to add on. And the second one, it allows people to just use the other model on the MacBook. And also we welcome to more contributions from the community, like fine-tuning on the small-scale language and the model quantization running on CPU to make it faster. And also, our company is actively hiring, and if you are familiar with those stuff and you're interested in us, just to click our website and to see if you like to work in this area, and we welcome your feedback and your suggestions and all the things related to either the models that we released and or the products that we have already published. Yeah, I think that's all to our presentation, and we welcome to any questions from.
Amazing. Let's go to Q&A. I mean, first of all, like before, because there's a delay between us and the live stream, and I think before we getting the question from YouTube and X and also LinkedIn, I think general the question that I have is because you support like, over 100 kind of like languages, and also probably different dialect. Like, what's some of the interesting example you tried it yourself like during development? I'm pretty sure you're going to have some amazing example.
The examples actually is hard for us to evaluate because we only know the Chinese and English. And we also need the help from our colleagues to judge if the audio is authentic enough. But one thing that bothers us a lot is because we are Chinese and we have the strong accent, and we hope that after we're doing the voice clone, the English accent, we will not have the Chinese accent when we speak when we clone our voice in English. But unfortunately, we will still hear very strong Chinglish after we do the voice clone. I think this is.
But do you think that's a good thing or bad thing? Like, because it's like very faithful to like your how you speak like normally, right? Because are this a bad thing or or good thing?
We are happy for the model, but sad for ourselves. Since we cannot clone the authentic English pronunciation, but I do think that could be an opportunity in the future, since how to control how the authentic that you want, and how much that you want to achieve the naive accent of your clone voice, with a little bit sacrifice of your own accent.
I see. Yeah, and I'm pretty looking for like if like you have like I'm pretty sure you're going to have like API, and also like do you have like configuration kind of like parameter you can tune, like I'm leading toward this kind of accent, I'm leading toward this kind of language. Do you have some configuration like that for your API or other kind of like input for the model to control,
Yeah, I mean, for the accent control, I don't think we have that one, because currently we didn't put too much attention on those fine-grained thing. I mean, because the accent is more fine-grained than the language itself, right? But I think you could, the developer could just click our doc page, and we already try to put every detail set how to use our model there. And to clone voice, I don't think you need to specify the language code if you don't want to, because we will directly detect from the target text that you're then generate the correct output.
I see. How about Huapeng? So are there some of the interesting example you try with the
actually,
yeah, wait, separate.
Actually, my colleague Sining has shown me some interesting sample which he make the TTS can sing. Remember the sample? I think it's a song called "So Call Me Maybe." Yeah, that song. And it's just like a symbol tag, and if you make the reference audio to which is singing, and you input the "Call Me Maybe," it will just like "So Call Me Maybe," just like that. I think it's quite interesting.
I see. I mean, right now, you're one of the most popular TTS model at Hugging Face, and I'm pretty sure that there'll be a lot of people actually using that right now. So did you get any like feedback from the community, like so what could be the next improvement for the model, or like what's some of the like interesting application you see, like beside the voice agent stuff? Do you seeing some community signal from that?
Yeah, I think there is one guy who want to who contact the Boson, and Nancy sent that to me, which called Rick Ross, and Rick actually asked him if he's a rapper, because there is also a rapper called Rick Ross, and then he is like a do a single person company, and which can want to use our model to generate some maybe fluent and streaming voice. But actually the open source one is now non-commercial. So but actually I think he has some good case. I'm not sure what he doing, but yeah, but I think there are some good example from Ke which helps disability.
Yeah. We hear a story from a user, and he mentioned that he lost the capacity to see some words clearly. So he just tried our model and found that it could actually reproduce his voice in a clean way, and he could use our model in his. I mean, he's a content creator now, and he tried to use our model, and it looks surprisingly good to him.
Amazing. Yeah.
And our team is cheered up by that person a lot. And we do hope that if such kind of person could help people with some disability in pronunciation, I think it will be. I mean, we will be very happy like to help them, and even help them to make their voice better by doing more techniques like deep cloning.
Mhm. Okay. I think I got one of the question from Slack channel. So basically they ask like why you use Q and 4B as the base model. Is that any reason why you choose a 4B model for a TTS? Because like 4B is quite huge for a TTS model, right?
Mm-hmm. Yeah, good question because Q and do have a few different skills, but we want to provide the best to the community, and usually a larger model comes with a better capacity on doing the harder tasks. So that's why we want to release this version.
I see. I see. Um, also get something from Max asking like so basically you open source a TTS, right? So do you like consider like some kind of like issue like safety like people to use that for doing scamming on the phone and also like doing some some material that is like not supposed to that kind of situation. So do you implement some guardrail to like to not let the model to output or clone outcome like that? Or how about the safety part?
You mean for the API, right?
API also like for the model itself is do you do something about that?
I I think for the model itself, I'm not sure this part. I mean, do we do the
I think
safeguard?
actually it's pretty hard. Yeah, in the alignment, we add some safety alignment to the to make the model. I mean, pronounce things in a correct way, but honestly speaking, this part is hard to do in the modeling side because we are not like a language model that could control the things that it generates to be safe. We are just a text to speech model. We want to faithfully transfer the input to the output.
I see.
But in the future, I mean, currently we are working on a lot of relevant things like the API or even the avatars, and we try to add more safety guarantees to that. And I think we already implement some basic one, and we are trying to make it better.
I see. This is amazing. Yeah. We're a little bit over 1 hour. I think we can get a one last question. So also from the Slack community, let me check. So basically people asking about okay, you support over 100 languages. Like how do you select those languages? Like are they say purely like driven by the data you have, or people just like curious like how do you select those languages?
I think both, but the frequency of the user just comes with more priority.
I see. I see. Yeah, I think we also have something from the YouTube. Let me try to bump it up. Actually, from Boson AI. I think it's one of your colleague like showing one of the user feedback. So yeah, it's saying that Higgs Audio 3 is the best text to speech for this language. Genius, impressive work. Yeah, we would love to like see people to like that use a underrepresentative languages. They actually use that for like audio agent and other stuff like that. Yeah, I think that's it for today. Again, like thank you so much, Huapeng and Ke, for showing your work and also your optimization for SGLang and the support to SGLang-Omni. And a little bit quick run over to our community. So if you have not joined our community, we have GitHub pages and repo SGLang. We have over 70,000 community members, so feel free to join us and be part of the community. So we have a contribution guide. Let's build the open frontier AI together, AI infra together. And also we have a X account called sysorg. And wait a minute. So right now, the XGLang project account is back. So please follow. We're going to share our version release, office hour like this, and tutorial video, community spotlight, and even updates on that account. So this account is going to be our community account, and sysorg account will be more focused on the actual technical block and other important stuff. Again, we have a course about SGLang at Deep Learning AI. Feel free to check out. It's a little bit over 1 hour, but you teach you basic thing about SGLang. It's good enough for you to start to learn about modern LM inference. Final things. Again, we have a Luma calendar. So if you need to know, the offline meetup and also the online office hour like this in the future, go to luma.com/SGLang. Subscribe to the calendar. All right. Thank you so much, Ke and Huapeng, again for joining us today, and thank you so much for people who watch us from X, LinkedIn, and YouTube. Thank you so much, and see you next time.
Yep.
Yeah,
Bye.
thank you.